And there are two different types of friction. The first of which is called kinetic friction. Okay, and that's an object or friction that opposes an object's velocity. Okay, it opposes an object's velocity. So kina or kinetic, what does that word lead you to believe that it means? What is kina? What does that prefix mean? Yeah, kinematics. Anything else that? Kinetic. Okay, what are those words? Do they lead you to something else?
Kinetic friction.
Yeah, what do you think?
Kina means movement.
Kina means movement. That's right. So kinematics are equations for objects in motion. Kinetic friction is friction of an object that's in motion. So kina means motion. So in order for something to have kinetic friction, our object has to be in motion already. Okay, so it's opposing our velocity. So whatever way we are moving, our friction is always going the opposite direction. Okay? The size, when we say magnitude, that's the size. So the size of our kinetic friction depends on the nature of the two surfaces that are interacting. Okay, so when I say two surfaces that are interacting, that means like if I'm rubbing or if I'm sliding sandpaper on carpet, would you expect a lot of friction? Yes, right? But if I'm rubbing an ice cube on ice, a lot of friction or no? No. So the amount of friction not only depends on kind of the size of the object and all that kind of stuff, but it also depends on the two surfaces that are interacting with each other. So the two surfaces that are doing the sliding or colliding or whatever you want to call it. Okay, the interaction. Okay. Kinetic friction or friction in general has found to be proportional to the normal force. Proportional to the normal force. Okay. So here's our equation for friction, and I'll write it a little bit bigger here so you can see it. Force of friction is equal to the coefficient times the normal force. Okay, and this little k subscript here just means kinetic friction. We'll look at the other type of friction here in a second. But essentially the equation for friction is the same in both cases. So you're going to take friction equals coefficient times the normal force. So this would be an equation that you might want to have on your equation sheet.
So that would be coefficient.
Yeah, this means a coefficient. It's like a Greek letter. So it's kind of like a U with a tail on the front. Okay, and coefficients, they depend on the two surfaces that are interacting. So there's going to be different coefficients of friction for ice on ice and wood on wood or metal on something. You know, there's different coefficients depending on the surface. Force of friction equals coefficient times the normal force. To demonstrate that our frictional force is coefficient or is proportional to the normal force, I want you to take your hand and just rest it lightly on your table. Not really pressing down, not really lifting up, just press it lightly on your table and try to slide your hand. Difficult or not so difficult?
Not so difficult.
Right, not a whole lot of friction. But as we increase the normal force, so push down on the table, that would cause an increase in the normal force. Now try to slide your hand. Okay, push down and increase the normal force and try to slide your hand forward. Much more difficult, right? Okay, so that increase in the normal force means that we have an increase of those two surfaces interacting, which would cause more friction, right? And if we lift our hand off the table a little bit, right, it feels kind of frictionless. Right, we're decreasing the normal force, so we have less friction. Okay, so you'll see a relationship between the normal force of an object and the friction. Okay, static friction is our second main type of friction. And what's it mean if something is static? It's still. Is it moving or not moving? If something is static or stagnant, right, they're not moving. So static friction means it's the frictional force that's acting on an object at rest. Okay, it's acting on an object that's at rest. So kinetic friction is an object in motion. Static friction is an object at rest. Okay, so we have to overcome static friction in order to put it into motion. Okay, you would never have kinetic friction and static friction at the same time. Right? So once we overcome static friction, we put it into motion, now we're dealing with what type of friction? kinetic, okay? I'm going to tell you that there's not a huge difference in solving for these two things, so you don't need to get caught up on that part of it. You're solving with the same equation, okay? And so really, your book labels it as F max because this is the maximum amount of friction that we could have, but I still want you to use the same equation for both types of friction. Okay, so this is no different than the equation you just previously wrote down. This would just be the coefficient of static friction instead of the coefficient of kinetic friction. Okay, so if you turn to page 96 in your textbook, I'll put that back up there. It's the same equation that you just wrote down. So if you turn to page 96, it's a little U with a tail on the front. It's a Greek letter. I think it's called mu. Page 129. Okay, so instead of page 96, sorry, page 129 in your book has coefficients of friction for both static and kinetic. So which of these coefficients do you think would be larger? The coefficient of static friction or the coefficient of kinetic friction? How many of you think static friction would be larger? How many of you think the coefficient for static friction would be larger than the coefficient of kinetic friction? Static, raise your hand. Kinetic, raise your hand. Okay, good. Your static friction should be larger because it's harder to get something started than it is to keep it moving. That makes sense? When you're pushing something, it's harder to get it started than it is to keep it in motion. So if you look on page 129, there's a little table, 5-1, and it says coefficients of kinetic friction, or coefficients of friction, both types. Rubber on dry concrete has a coefficient of 0.8 and 0.65. So these coefficients have been assigned based on the two surfaces that are interacting. So the coefficients will be either given to you or you'll have to solve for them. Okay, it's not something that you have to memorize. Okay, you don't have to memorize coefficients of friction.
So like on a test, it'll be like, so the coefficient of rubber on...
Yeah, it'll tell you, the coefficient between these two surfaces is these, it would tell you that. Or it would ask for what is the coefficient of friction. But you don't have to memorize coefficients of friction. Okay?
What does that stand for?
Force of friction.
So you would say like the coefficient will find the force of friction.
Yep. We're going to do lots of each of those. Okay, but the static friction coefficient should be larger than the kinetic friction coefficient because it's harder to get something started than it is to push it once it starts, once you get it going. Okay, let's try one here. A sled has a mass of 50 kilograms, is pulled horizontally along a flat snow-covered surface with a force of 75 newtons. The coefficient of kinetic friction is 0.010. Okay, so our goal is going to be to find the acceleration. Okay, so I kind of walked you through the several steps it's going to take to get there. But I want to just look at the actual final part, which is the acceleration. It's a lot of steps, but it'll get there. Sorry. Okay, so we're solving for the acceleration. That's going to be our overall goal. So like all force problems, what should we do first?
Write everything down.
Write everything down, draw our free body diagram. Okay, free body diagram first. So I'm going to put it up here. Gravity's always acting. Normal force is acting. We've got some applied force because it says it's being pulled horizontally along a flat surface with a force of 75 newtons. So that's going to be our applied force. Would we agree with that? Okay, and it gives us our coefficient of friction, which means we have to know that there is a friction force. Okay, does that part make sense? So whenever it includes the coefficient of friction, or if it asks for the coefficient of friction, that means we need to include friction in our diagram. Okay? So does this free body diagram make sense to everybody? Okay. This sled, as we're dragging it horizontally, is it moving vertically at all? No, so what's that mean about our normal force and our gravitational force? They're equal to each other. Okay, so that's going to be the first thing I do. Okay, I'm going to find out what Fg and Fn are equal to. Okay, because I'm going to have to know the normal force in order to find friction. Wouldn't you agree? Okay, since friction is coefficient times the normal force, I'm going to have that. So I'm going to take 50 times 9.8. And I think I get, what, 490, something like that? Why don't you check my math on that? Okay. 490 newtons. Okay, so now I know gravity is 490. I know that my normal force is 490. So I want to find my horizontal acceleration. So now I need to set up my net force equation.
What is that F for before the G?
Right here?
Isn't it math?
That's just force.
This is just force of gravity. So yeah, you're right. It's m times g. I just did Fg equals mass times gravity. I just left them as Fg for right now. Okay, so in the x direction, my horizontal net force is equal to my applied, which was 75, minus my force of friction. Okay, are we on the same page with how that equation came about? Positive forces minus negative forces.
Yeah, I have a question.
Yeah.
Why do we have to find the vertical force?
Why did we have to find the normal and the gravitational? Because in our frictional force, what can we substitute for a force of friction? Coefficient times the normal. So we're going to substitute coefficient times the normal, which is why we had to solve for the normal force in the first place. Good question. Mass times acceleration is F net. Okay. So our frictional force, I think they gave us the coefficient, so I'm going to just erase that and put in my coefficient. And they gave us, or we solved for the normal force already, so I'll go ahead and just plug in those numbers. Sorry, this says 490 right here.
Why is 490 in the negative section?
We used 490 because it's the normal force. So when we solved for the frictional force right here, we take the coefficient, which is 0.010, times the normal force, which was 490. So that's where this came from. So did we get our acceleration at 1.4? Yeah, 1.402?
The frictional force always has to be less than normal.
Okay, so these are kind of the general steps that we took. We found the force of gravity, then the normal force, and then that allowed us to calculate the force of friction, and then we were able to plug it in and solve for the net acceleration. So yeah, these steps will usually take you through most problems. So try this one on your own. Okay, very, very, very similar to the one that we just did.
Burrito?
Wrong.
Oh, this is so overhyped.
Their ice cream is so good.
Yeah, what's with this ice cream?
All I ever get was so good.
A 30-kilogram box is sitting on a wooden floor. A girl pulls upward on the box with a force of 100 newtons at an angle of 40 degrees. The box begins to slide, despite that the coefficient is 0.3. So we're going to find the horizontal acceleration. Here's the steps that you need. This one is more complicated, okay, in a couple ways. What'd you say? Yeah. All right, we're going to have to go kind of super speed here to get through this one. All right, so try to stay with me. Gravity, normal. Here's our applied force at 40 degrees. Okay, I'm missing one other force. What is it? Friction. So friction, gravity, normal. And it says that my pulling force was 100 newtons. Okay, so in this case, is my normal force and my gravitational force equal to each other? Yes or no?
No.
No, right? This right here, my F applied Y, throws it off, right? Because I'm lifting up on that box a little bit, so I'm taking some pressure off the normal force. So those two are not equal to each other. Okay, so first thing that we need to do anytime we see something with an angle, we need to break it into its X and its Y. Okay, we don't have to necessarily follow these steps 100%, or I didn't include that first step, I don't know. Okay, so let's solve for F applied Y.
It's K. It's kinetic.
Yeah, that's just the coefficient.
Okay, I'm blind. I just can't.
That's okay. So to find Y, is that going to be sine or cosine? Good, 100 sine of 40, and then for X, we're going to do 100 cosine of 40. Okay, and both of those components are going to be positive. 64.3 and 76.6. Okay. So now, are we ever going to use that 100 anywhere in our problem? No, we will not. So once we solve for it, just get rid of it. Okay, you're not using it anymore in your problem. Once we break it into its X and its Y components, we won't use that angle or that size of 100 newtons again. Okay? So now let's solve for FG. That's the next thing that we can solve for. And how do we solve for force due to gravity? Mass times gravity. Mass times 9.8. Okay, thank you. So we took 30 times 9.8, and we get 294. Okay, so we're on our way here. Okay, we found the force due to gravity. Next, we need to find the normal force. Okay, so is a normal force, is it a horizontal or a vertical? Vertical. So let's set up our net force equation for the vertical direction. How many vertical forces do I have?
2.
No. 3. 1, 2, 3. Okay? So I would say normal plus F applied Y minus gravity. Okay, do we see why all three of those forces have to go in there? Okay, all vertical, so upward minus downward. The net force in the vertical direction is what? 0, because it says the box begins to slide. So it is not accelerating in the vertical direction. So that's 0. We're solving for the normal force. We know F applied Y is 64.3. And we know force due to gravity is 294. Okay, so go ahead and solve for the normal force there.
Are we ever going to do anywhere it doesn't begin to slide?
Like where we lift it off the ground?
Live?
It's possible. Okay, so we found the gravitational force, we found the normal force. Now if we go to find the frictional force, how do we do that?
One more time, coefficient.
Yep, coefficient, which is 0.3 times the normal force, which is 229.7. So now I'm going to set up my net force equation in the x direction. How many horizontal forces do I have? 2. So I'd say F net equals F applied x minus the frictional force, and then I can just plug in the numbers that I have. 68.91, and F applied x is 76.6. That's going to be equal to mass times acceleration.
How did we know that it was the north of south angle opposed to the,
Oh, this one right, this angle right here?
not south, I meant
That's okay. Anytime it tells us that we're looking at something horizontally, we just assume, or like this box is resting, we're just assume we're pulling it upward in the positive direction. You won't see any other angles besides that. Okay, so I promise on these ones, I'll never give you a different type of angle. It'll always be north of it. Yeah, always. Okay, from the horizontal, it'll move up. That'll always be that angle. So our acceleration here is, yeah, good. Sorry, I'm writing it where I can't write. Acceleration equals 0.256 meters per second squared.